Come on, guys, we're almost there. I know it's been an hour. Just stick with me. Come on, your brain hurts, but you're learning. Let's go. Last problem. Problem 3, 2012, Amy 2, number 15. Wow, inversion killing late Amy problems. Triangle ABC is inscribed in circle omega with AB equals 5, BC equals 7, AC equals 3. The bisector of angle A meets BC at D and circle omega at a second point E. Let gamma be a circle with diameter DE. Circles omega and gamma meet at E and the second point F. Then AF squared equals M over N. Find N plus N. Alright, so there's a lot of ways you can go through this. You can do a lot of law of cosines bash, Pythag bash. There's also something nice here because they deliberately contrived this problem so that BAC is 120 degrees, so that BEC actually becomes an equilateral triangle, and then you can continue from there. But now it turns out there's actually an inversion problem, and some background to this problem. It turns out there's another problem from the, if I'm not wrong, 2009 Russian Olympiad. That's the exact same problem without the numbers. In particular, we wanted to show something. I'm not going to give it away yet. They use the same exact configuration, no numbers. So, Amy, you can't do that. But anyway, that's why some people might have solved this with inversion, because 2012 is after 2009. Anyway, let's see. So there's an angle bisector, there's triangle ABC. Come on, you guys know the drill. We're gonna use our force overlaid inversion, root BC inversion, and then reflect over. So let's see what happens. I might not need this slide, but yeah, no, let me use it. So we're gonna draw a circle. I'm gonna use a different color. A, B, C. Okay, this doesn't look like the circle in the problem. This shouldn't matter too much. We'll use the lengths in the end because we need to prove a crucial observation first. This crucial observation is the same that we had to prove in that Olympiad problem. D, that's a D. Okay. Okay, so I actually included M, the midpoint of BC, in this problem because it's important. And then F. So, wait, I think, okay, that's a bit messed up. One important thing is that because of the angle bisector, E is actually the midpoint of BC, arc BC. And since M is the midpoint of BC, EM is perpendicular to BC. That doesn't look like in this diagram. So that means, because DE is the diameter, that means M actually lies on this circle, gamma. Okay? That's one important observation. Now, what's going to happen when we use our force overlaid inversion? Well, so we're gonna have our C prime and B prime. On the circumcircle of A prime, B prime, C prime, since M lies on BC, M prime is gonna lie on the circumcircle of A, B prime, C prime. So, and then when we reflect back, M prime is in fact just gonna be the extension of M prime onto AM onto the circumcircle. Now about the length. No, we know AM prime equals AM prime equals AB times AC over AM because of inversion definition. Hold on, no, actually, that's not true. M does not go to M prime. Sorry. I'm very sorry about that. M actually goes to, what's gonna happen? Since, M prime was reflected over the angle bisector, so since M prime lied on AM before, when we reflect over the angle bisector, AM prime is actually now gonna go to some point here. M prime. This distance is the same though, because reflections. So we can keep this here, but this is not M prime. Now, just like our last problem, we showed that D and E are just going to invert to each other, right? So indeed, the circle is going to invert to itself, because diameter is DE. Now, since M prime is, we can actually redefine it to be the intersection of gamma with BC. When we invert it and reflect, it's going to become this M prime is going to be the intersection of circumcircle ABC with this diameter. Does that make sense? Because in here, DE would remain the same in this AB prime, in AB asterisk C asterisk triangle. M prime lies over somewhere here, and so it should be the intersection of diameter DE circle with circumcircle AB prime C prime, and now when we reflect, we're gonna move it over here. But it's gonna be back to the original over here. Alright? But F was actually defined to be the intersection of DE with ABC. So diameter DE circle with ABC. So that means M prime equals F. Okay? That means AF equals, and F, this all implies that AF is the symmedian, but you don't necessarily have to know symmedians to know to proceed. But still, symmedians are good to know. Anyways, we have AF is just AB times AC over AM. Now this is just pure computation. We know AB, we know AC. We just need to find AM, but this is actually easy with Stewart's theorem. So by Stewart's theorem, we're going to find AM squared. Remember a mnemonic. A man and his dad put a bomb in the sink, right? So D is going to be AM squared times A, which is 7, plus man, which is M times A times N, which is 7 over 2 times 7 over 2 times 7. 7 over 2 times 7 times 7 over 2. Sorry about that. Oops, blue on blue. I know that been such a good decision. Equals BMB, which is 9 times 7 over 2, plus CNC, 25 times 7 over 2. Now we're going to divide by 7 over 2. And this becomes 2. And AM squared equals 34 minus 49 over 2. 2 times So 34 minus 49 over 2. That is, what is that? Sorry, my computation is slow. 19 over 2. That was kind of slow. So am squared equals 19 over 4. And am is thus root 19 over 2. We're going to plug that in here. AB times AC over AM equals 3 times 5 over 19 over root 2. No, root 19 over 2. Which equals 30 over root 19. I think I know what to do now with this. Oh, apparently I don't. Anyway, we're basically done. 30 over root 19. Now, when we square, AF equals 30 over root 19. So we square, and thus, come on, go with me, go with me. We get our answer of AF's, 900 over 19. With the final answer of 919. And we win. Amy number 15. Alright, that's our last problem.